Okay, so this video is on network reduction and the Hungarian algorithm. These are optimization techniques, and what we're going to do is we're going to have a look at two examples. This first one here is a network you could be presented with. What we're trying to do is find what's the minimum cost of this relationship B, F, T, and G, and H, O, W, O, C, O, and L, O. So these could be people, and these could be how far it is to get to places, or how much it costs to get different things. Anyway, it's a system, and we're going to try and find the minimum cost. That is, the minimum combinations of B buying something, F buying something, T doing something, and G doing something. So what we do is we reduce the rows first by taking away the smallest number from each row. So in this case it's going to be 4. So I'm just going to rewrite out the network over here without these letters on the side or up the top. So we're going to take 4 away from each, so it's going to be 11, 3, 0, and 7. The next row, the smallest, is 8, so we take 8 away, and it's going to be 15, 0, 0, and whatever the heck that is, 14. Then 7, we'll take 7 away, 10, 8, 0, 10, 8, 0, and 5. And then lastly, we'll take 2 away, so 6, 0, 6, 0, 8, and 9. Now we can see that this column and this column don't have any zeros. So first you do the rows, taking away the smallest number you can. Then if there's columns without zeros, we need to take away the smallest number from each column. So in this case the smallest number is 6. So we rewrite out this column as 5, 9, 4, and 0. And we rewrite this column out as 2, 9, 0, and 4, because in this column we're taking away 5. In this column we took away 6 because that was the smallest number. These other numbers, their columns already had 0, so we just copy them down as they are. So 3, 0, 8, 0, and then down this way 0, 0, 0, 8, 0, 0, 0, 8. Now in this version of network reduction, we've reduced the network using column and row reduction, or row and column reduction. In this version we can actually tease out an answer to the optimized network straight away, because if we look here, there's only 1 0, and if we box that up and then go down to the next row along, it's almost as if we've given this task to this person. You see over here we've given that task to that person. The 0 was in the 3rd position along in the top row, 3rd position along in the top row. And if we go down, if that task has already been taken, then this one, which had 2 zeros, that task has already been taken. Give this task to that person. If these two are already taken, then this can go to this person, because that one's already been used up in that column. And lastly, that one's already been used up in that column, left over one there. So we can now go across and assign positions to each row. So that one was taken there. This one's the second one along, so that's that one there. This one's the 4th one along, sorry about that. 4th one along, that one there. And the first one, that one there. Look, sometimes you'll find there are bipartite graphs which go with these things here. How do they work? Well, we'd have the B, F, T, G, the B, the F, the T, and the G, and we'd have the W, the HO, the WO, the CO, and the LO. And what we do is we'd look along and we'd say, all right, that has 1 0, so that belonged to the B row, 1 0 at CO. So B to CO. F had a 0 at the third one along, which is WO. Now, then we had, but F also had a 0 going to there. Now, when we're first making up a bipartite graph, if we haven't decided who gets what, we just draw lines to all the zeros. So this one had 1 to WO and to CO. We can see it, WO and CO, WO, CO. So that also goes to CO. Then this one had 1 to CO and the last one LO, so CO and LO. And then finally the last one had 1 to HO and to WO, so HO and WO. Lots and lots of lines there. I think the important thing really is this process of row reduction and then column reduction. They're the important things. And then assigning by using a bit of logic and reasoning. Okay, so the minimum weight then, or the minimum cost for this would just be these 4 boxes added together. So that would be 32. So 4 plus 8 plus 12 plus 8. Okay, let's have a look at a slightly trickier one. Why don't you go ahead and pause the video and try doing your row and column reduction, see what you get, and then come back and see if we get the same answer. Alright, so I'll start my row and column reduction. Alright, so 32 is the smallest number in the first row, so we take 32 away from everything, and that would make 5. 25, yeah, sorry, 5, 25, 36, and 0. In the next one, 54 is the smallest, so we take 54 away from everything, we get 10, 0, 18, and 42. Next row, we've got 38 is the smallest, so we'd get 43, 0, 18, is that right? Yep, 18 and 24. And then the last row, 35 is the smallest, we take that away, we would get, come on brain, we get 2 zeros there. Oh dear. What is that? 20, 25, 27. Yeah, got there in the end. And 30. Okay. So we've got our rows done. But then if we look here, this column has no zeros. So what I'm going to do is take 5 away, because that's the smallest number, 5 away from all them, so that becomes 0, that becomes 5, that becomes 38, and that becomes 22. Alright, we've done our row and column reduction, but in this case, we can't just logic our way through and assign things. There's 2 zeros here, but so we can't really say, there's 1 0 here, but if we block that one out, there's also 1 0 here. So which one is the one that we've got to block out first? We can't tell yet. And because we can't tell, we have to apply what's known as the Hungarian algorithm. Okay, so this is quite tricky, so pay attention. We have to first draw the minimum number of lines that would cross out all of the zeros we've got. So if I draw a line across here, I draw a line across here, and I draw a line across here, I've covered all the zeros, and thankfully we can still see them hiding behind there. The things we're interested in now are the numbers that have been crossed in both directions, and the numbers that have nothing done to them. They haven't been covered, crossed, or drawn over at all, have they? So first we're going to look at the uncovered numbers, and out of those uncovered numbers, which is the smallest number? The smallest number this time is 5. So what we're going to do, all the uncovered numbers, we're going to take away 5 from all of them. So let's just start with that. We're going to go 0 and 33. And I'm trying to put them in the same position, so that's going to become 13, 13, 37, and 19. Now, the other special ones are the ones that have had crosses on them. If they've been crossed in both directions, see that smallest number we had before, we're going to, just like we subtracted it from all the uncovered ones, we're going to add it to the covered, the crossed ones, but only the crossed ones. So 30 and 5. All the other numbers that have been covered just once, we do nothing to them, we just copy them across. So that was a 0, that was 36, that was a 0, 0, 0, 22, 0, and 30. Now that process, if it doesn't give you an answer straight away, you repeat that process again and again and again. What process was that? Covering the zeros with as minimal lines as you can, finding the smallest number that hasn't been covered at all and subtracting it from all the uncovered numbers, and then any crossed numbers, adding that smallest number to them. And that process is the Hungarian algorithm. In this case, we can actually tease out our answer. We have a 0 here, we have a 0 here, so both of those rows have been sorted. And then because this one has been decided upon, this column can now no longer, we ignore any other zeros in that column. So then we can say that that one, and again that one blocks out that 0, and that one. And that means we can come to our, we can make our bipartite graph first. Actually, let's not bother with that. Let's instead just say this is our minimum weighting. This is our minimum weighting. So that one, this one, and this one. And we add those 1, 2, 3, 4 numbers together. 32, 64, 38, and 35. So 32 and 64 is 96, 99, and 129, 130, 134, 164. Okay. Hooray! And that is the minimum assignment we would need to optimize this network. Okay, we can practice that some more this week and try it out on MathSpace. Thank you.